Prepare to be captivated as we unveil the untold story behind NASA's groundbreaking RS-25 engine in this riveting video. Journey with us through the corridors of innovation as we uncover the real reason why this marvel of engineering was developed. Brace yourself for a tale of ambition, determination, and the relentless pursuit of human exploration. Get ready to witness the convergence of cutting-edge technology, reusability, and the quest for spacefaring excellence. The Aerojet Rocketdyne RS-25, also known as the Space Shuttle Main Engine, SSME-OWN, is a liquid-fuel cryogenic rocket engine that was used on NASA's Space Shuttle and is currently used on the Space Launch System, SLS. Designed and manufactured in the United States by Rocketdyne, later Pratt & Whitney Rocketdyne and Aerojet Rocketdyne, the RS-25 burns cryogenic liquid hydrogen and liquid oxygen propellants, with each engine producing 1,859 kN, 418,000 luff, thrust at liftoff. Although RS-25's heritage traces back to the 1960s, its concerted development began in the 1970s with the first flight, STS-1, on April 12, 1981. The RS-25 has undergone upgrades over its operational history to improve the engine's reliability, safety, and maintenance load. Components. The RS-25 engine consists of pumps, valves, and other components working in concert to produce thrust. Fuel, liquid hydrogen, and oxidizer, liquid oxygen, from the Space Shuttle's external tank enter the orbiter at the umbilical disconnect valves and from there flowed through the orbiter's main propulsion system, MPS, feed lines, whereas in the Space Launch System, SLS, fuel and oxidizer from the rocket's core stage flowed directly into the MPS lines. Once in the MPS lines, the fuel and oxidizer each branch out into separate paths to each engine, 3 on the Space Shuttle, 4 on the SLS. In each branch, pre-valves then allow the propellants to enter the engine. Turbopumps. Oxidizer system. The low-pressure oxidizer turbopump, LPOTP, is an axial flow pump which operates at approximately 5,150 revolutions per minute, driven by a 6-stage turbine powered by high-pressure liquid oxygen from the high-pressure oxidizer turbopump, HPOTP. It boosts the liquid oxygen's pressure from 0.7 to 2.9 MPa, 100 to 420 psi, with the flow from the LPOTP then being supplied to the HPOTP. During engine operation, the pressure boost permits the high-pressure oxidizer turbine to operate at high speeds without cavitating. The LPOTP, which measures approximately 450 by 450 millimeters, 18 by 18 in, is connected to the vehicle propellant ducting and supported in a fixed position by being mounted on the launch vehicle structure. Fuel system. The low-pressure fuel turbopump, LPFTP, is an axial flow pump driven by a 2-stage turbine powered by gaseous hydrogen. It boosts the pressure of the liquid hydrogen from 30 to 276 C, 0.2 to 1.9 MPa, and supplies it to the high-pressure fuel turbopump, HPFTP. During engine operation, the pressure boost provided by the LPFTP permits the HPFTP to operate at high speeds without cavitating. The LPFTP operates at around 16,185 revolutions per minute and is approximately 450 by 600 millimeters, 18 by 24 in size. It is connected to the vehicle propellant ducting and is supported in a fixed position by being mounted to the launch vehicle structure. Development. The history of the RS-25 traces back to the 1960s when NASA's Marshall Space Flight Center and Rocketdyne were conducting a series of studies on high-pressure engines developed from the successful J-2 engine used on the SD and SIVB upper stages of the Saturn V rocket during the Apollo program. The studies were conducted under a program to upgrade the Saturn V engines, which produced and designed for a 350,000 pounds, 1,600 kN, upper stage engine known as the HG-3. As funding levels for Apollo wound down, the HG-3 was canceled, as well as the upgraded F-1 engines already being tested. It was then designed for the HG-3 that would form the basis for the RS-25. Meanwhile, in 1967, the U.S. Air Force funded a study into advanced rocket propulsion systems for use during Project Isinglass, with Rocketdyne asked to investigate aerospike engines and Pratt & Whitney P&W to research more efficient conventional de Laval nozzle-type engines. After the study, P&W put forward a proposal for a 250,000 pounds engine called the XLR-129, which used a two-position expanding nozzle to provide increased efficiency over a wide range of altitudes. The reason why NASA made the RS-25. The development of NASA's RS-25 engine, originally known as the Space Shuttle Main Engine, SSME, stemmed from a multitude of factors and goals that coalesced into a significant undertaking. At its core, the RS-25 engine was designed to power the Space Shuttle, the iconic spacecraft that served as NASA's workhorse for 3 decades. However, the real reasons behind its development extend beyond just the needs of the Space Shuttle program. One key reason for developing the RS-25 engine was to achieve the demanding performance requirements necessary for human spaceflight. NASA sought an engine that could deliver a high level of thrust while maintaining reliability and safety. The RS-25 engine fulfilled these criteria, generating an astonishing 512,000 pounds of thrust and boasting a remarkable level of redundancy and fault tolerance. Its development was driven by the imperative to ensure the safe transport of astronauts and cargo into space. Another crucial aspect of the RS-25 engine's development was its reusability. NASA envisioned the Space Shuttle as a reusable space transportation system, and the engine played a pivotal role in achieving this goal. The RS-25 engine was designed to be reusable, to refurbish and reuse the engines multiple times to reduce costs and enhance the sustainability of space operations. This reusability aspect was vital in NASA's efforts to create a more cost-effective and efficient space transportation system. Moreover, the RS-25 engine was developed with a focus on advanced engineering and technological innovation. NASA aimed to push the boundaries of rocket engine technology, incorporating cutting-edge materials, manufacturing techniques, and computer simulations. The engine's design utilized regenerative cooling, where fuel was circulated the engine's nozzle and combustion chamber to cool them during operation. This innovation maximized engine performance and efficiency, enabling the RS-25 to deliver exceptional thrust while enduring the extreme conditions of space travel. Additionally, the development of the RS-25 engine served as a stepping stone for future exploration endeavors. NASA recognized that the knowledge gained from building and operating the RS-25 engine would be invaluable for future missions beyond Earth orbit. It laid the foundation for the next generation of engines and propulsion systems, facilitating the advancement of technologies that would be crucial for deep space exploration, including crewed missions to the Moon, Mars, and beyond. As we conclude our enthralling journey through the captivating video on the real reason NASA developed the RS-25 engine, we are left with a deep appreciation for the ingenuity, ambition, and foresight that propelled this remarkable feat of engineering. Beyond its role in powering the Space Shuttle, the RS-25 engine represents the culmination of NASA's relentless pursuit of excellence in human spaceflight. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.